Okay, good afternoon. Good afternoon. So, we are still on that process of trying to understand how the universe works. It's a pretty good goal, I think. Why not try to get a really good understanding of how the universe works in a semester? We'll see how far we can make it. And right now what we're focusing on is the moving parts of the universe. If you want to know how the universe works, a good place to start is the how and why stuff moves part of the universe. And like I said last class, that's a big enough chunk of the universe that even if that's all we got done, and we're going to try to do more than that, you'd be doing pretty well. So we want to know how and why stuff in our universe moves. So that encompasses me and you and trains and planes and rockets and planets and moons and things like that. So that's where we are right now. We're trying to understand how and why stuff moves. Newton gave us some axioms or laws of motion, and that's a good place to start. So 1687, Newton says, I've got at least three, we might kind of include a fourth, maybe today. I've got at least three laws or axioms that describe how and why stuff moves. So for centuries or millennia, we want to know how and why stuff moves. Here is a document that lays it out pretty well. We still, for the most part, buy what he gave us in 1687. So the big one, and so like I said, there's three or four, the number in order doesn't matter, but the big one we started with is that everything in the universe has inertia. That's Latin for lazy. If it's at rest, it wants to stay that way. If it's moving, it wants to stay that way. Another way to think of that is everything in the universe has some state of motion. So whether you are sitting right now or standing or moving, whatever your state of motion is, that will stay that way forever without any outside influences. And as I've said, that's a little bit of a crazy statement because no one has ever watched something go on forever. But that's our understanding of the universe, that if something is at rest, it will stay at rest forever. If it's going that way at 10 miles an hour, it's going to go that way at 10 miles an hour forever. Which is crazy, because we don't ever watch something just go 10 miles an hour forever. Everything hits a wall, grinds to a stop, slows down, whatever. But it's true, and like I've said, now that we have astronauts and things, it's a little easier to believe, because at least on the space station, you can you can go watch YouTube videos of them messing around on the space station. They'll take even just a water droplet and get it going, and it'll just go in a straight line at a constant velocity forever. So everything in the universe has a state of motion that it'll keep forever until it's disturbed. Now, what we started talking about last class is what I mean by change your state of motion, and what I mean by that is to accelerate. So in this class, the word accelerate has a very specific meaning, and that means change your state of motion or change your velocity. So if something's at rest and I want to get it going, that's called accelerating it. If something's did I say that right? If something's at rest, I want to get it going, that's called accelerating. If something's going and I want to bring it back to rest, that's called accelerating. If something's going and I want to speed it up or slow it down, that's called accelerating. And in fact, if something's going this way and I want it to go that way, that's called accelerating. So any change in the state of motion we define as an acceleration. Or another way to phrase that, acceleration is the rate at which I'm changing the velocity. And as I said last class, velocity is the rate at which you're changing your position. So that's a lot of concepts right there, but it's important that all those make really good sense right off the bat. So I have my position right now. Let's call this 0. And right now, my velocity is 0, because right now I'm at, let's call this position 0. Right now I'm at position 0. Still there. So I didn't move. In 1 second, my displacement, my position did not change in 1 second, so my velocity is 0. So I'm not changing my velocity is 0. But if I want to get going, if I want my velocity to be non-zero, I would like to go over there, that's called an acceleration. I'm going from 0 meters per second, or 0 miles an hour, however you want to think of it, to some other speed that's not 0. Now I'm going 1 meter per second. Now I'm getting over there. Hooray. That took an acceleration. So for an instant, I accelerated. So I was standing here at 0 meters per second. I'm not moving. That's my velocity, 0. And now I'm going 1. for that little instant, I accelerated. I changed my velocity, went from 0 to 1. That acceleration had to come from a force. F equals ma. My m is 170 pounds, so like I said last class, I'm terrible at that. I think it's like 50, 60 kilograms. Divide by 2.2, whatever that is. So if I want to go from not moving to moving, I need a force. So that's kind of how, that's Newton's first two laws wrapped together, is that I'm at rest, I will stay that way forever. I will eventually get hungry, or some other class will come in here and I'll be in their way. So I need to get going. I get going by a force. And by the way, we'll talk more about this today or next class. That force wasn't me. I can't push or pull on myself. I got that force from the only thing I'm touching right now, and that's the floor. So the floor pushed me there. I got an acceleration. And that acceleration can be calculated. I don't know if we'll ever need to do that, but F equals ma. Okay. And so last class I was playing around with my velocity meter, different than a speedometer. Speedometers don't tell you direction. This one has a positive and a negative, so it'll tell me whether I'm going forward or backward. Away from the thing is forward, and toward it I think is backward or negative. So I've got my velocity meter up here, and the reason I have this up here is whenever possible I want, I can say a lot of words to describe something. Whenever possible, I want to be able to show you what I'm talking about. So if I want to show you acceleration, I really like these velocity plots. I like to look, I think they tell me I think they illustrate a little bit what's going on. So right now my velocity, let's see, where did dirt, sure, that, okay. Yeah, there's my velocity. Oh, now it's scrolling. All right. So right now my velocity is 0, so you can just see this. The data is just stuck right on the vertical axis. Now my velocity is about 1 meter per second, and it's there. But I think what's important is to notice the acceleration. Right now my velocity is negative 1 meter per second, hopefully. There it is. Okay. But what I also want us to see today is the acceleration, and the acceleration is the slope. Acceleration is the slope. You might remember from some other class. Slope is another word for rate of change. So the rate at which I'm changing my velocity can be seen up here as an acceleration. Okay. Let's do an eye clicker for fun. Stop doing that. All right. Okay. So this one's only A through D, and here's what I'm going to do. I'm going to stand in front of my little velocity meter. I'm going to walk for 2 seconds, and I'm going to come back. So this thing will transpire for 4 seconds. I'm going to walk for 2 seconds. I'm going to come back. I want to know what that's going to look like on the plot. And I guess the correct answer is probably E. None of those. It's going to be crazy all over the place. But I'm hoping it'll look like kind of like one of those. Yes. I'm going to run, come to a stop, and then accelerate back. Try to get back about the same speed I left. Maybe I just gave it away. right, 10 more seconds to vote. All right, and we're done. Should I won't show the results yet. Let's just try it. My mouse is so short today. Okay, I'm going to try it. Ready? Oh, wait, I'm going to stand out of the way. Yeah, sure, whatever. Ready? Go. Okay, that's what I was shooting for. The first, second is me getting up to speed. I have mass, so I can't instantly accelerate up to, I was trying to do B. So I couldn't instantly accelerate up to whatever that is at the top, 2 meters per second or something. I tried. I guess I could have stood out of the way. Let's try that. Let's see if I can do a little bit better. There we go. No, that's worse. Okay, that's worse. So that's what I was going for. I was going for a relatively constant acceleration. And so here's one of the things I wanted us to see there. Well, I want to see the whole picture. So I try to get up to some velocity, like 2 meters per second or so. And I have mass, so I can't do that instantaneously. I can't instantly go from 0 meters per second to 2 meters per second. That would be an infinite acceleration. Light can do that, but I'm not light. So it took me a second to get up to speed. Then once I got up to speed, here's what I was trying to do. I was trying to decelerate to 0 velocity and then accelerate the other way and then speed up. A couple things I want us to see there. That when I turned around, something about option C or D, your brain wants to see the plot turn around. So I eventually got to some point, I stopped, and I went the other way. And so I think the fact that I was turning around, something about my brain at least, wants to see the plot do the same thing. So C or D would maybe make sense. Now, when I turned around, actually all that I did was my velocity went from positive to negative. And for an instant, I was at rest. So I was going forward, we'll call that positive. My velocity slowed. I came to rest for an instant, and then my velocity went negative. So really, what the graph is doing is just going from some high velocity to, not that high, slow. In other words, getting closer and closer to that horizontal axis. Slow. It hits that horizontal axis. That means I'm at rest. That's the 0 velocity line. And then I start going the other way. All that means is negative velocity. So all you see is the plot just go through that horizontal axis. And so what you're seeing is a high velocity go to 0 and then go negative. And then I sped up in the negative direction. So I went from a little bit negative to more and more negative in the opposite direction. Okay, here's something else I want us to see about the plot. As I said, I'm not terribly concerned about the numbers of the plot. I'm just trying to visualize the world using a graph. I think it helps sometimes. So I'm looking at this plot to visualize what's going on. It's my velocity. And in that plot, not only am I seeing the actual value of my velocity, like 2 to 0 or negative 2 or whatever, I'm also seeing the rate of change, or the slope, or the acceleration. So my acceleration is the steepness of that plot. And so if I'm not changing speed, then there's no slope. It's flat. If I change my speed quickly, I have a nice steep slope. And so the slope tells me how quickly I changed my velocity. In other words, my acceleration. Now, one thing that I was trying to do, which in B was pretty hard to do, was do a constant acceleration. So this acceleration right there represents a constant negative acceleration. That's what because the slope doesn't change, right? If this was like hilly or something, if that plot was changed its slope, that would mean I was changing my acceleration. But what that plot represents is a constant acceleration in the negative direction. It's going down. Now, a couple other things to note about that. Constant acceleration in the negative direction. Here's what that means. I started going this way. As quickly as I could, I got up to 2 meters per second this way. Then I accelerated that way. Now, an important thing to note is you can do that. You can be going this way and accelerating that way. Because acceleration is just the change in velocity. So if I'm going this way 100, and then I accelerate this way 10, all that means is I just went from 100 that way to 90 that way. I'm still going that way. So you can accelerate in the direction opposite of motion. I think that's an important realization. So I started going 2 meters per second this way, and I'm slowing down, I'm decelerating, or another way to say that is I'm accelerating in the direction opposite my motion. I'm going 2, now I'm going 1, now I'm going 0, now I'm going -1, now I'm going -2. All of that was just an acceleration this way, the whole time. Yes, question? Great question. If I wanted to make it a positive slope, if I wanted to go upwards, I would have to accelerate this way. Let's try this. I would have to accelerate this way. Yeah, toward the thing, right? No, away from the thing. I have to accelerate away from the thing. So that's my initial. So right now I'm at rest. Right now I'm at rest. And if I speed up and go faster, 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 that's all acceleration up. That's all positive acceleration. Because I was in this classroom, we're going to call it to the right positive. So any change in velocity to the right is positive. Now, I tried to not be in front of the thing when I accelerated it initially. So I was behind here. Let me try it one more time. So I'm behind here. I'm accelerating, but then I started decelerating as soon as I got in front of it. So I kind of tried to hide my positive acceleration. But the very first time I did it, there you can see I accelerate positively, and then I accelerate slow, negative, 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 negative. But that first second is me speeding up. In other words, accelerating that way or changing my velocity in that direction. Because I'd hit the wall. Yeah. So so the question was, could I make a positive just that? Yeah, till I hit. So this is 4 seconds. So if I just took 4 seconds to slowly speed up, faster, 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 until I hit the wall. Darn, I went too fast. So I had to decelerate there in the last second. So I just got to go slower. Then I could accelerate for 4 seconds, and then you would see just that. Yeah. But that's me accelerating away from the thing for 3 seconds, and then I saw the wall coming, and I decelerated right at the wall. Okay. Any questions about that? Okay, I'm going to try the basketball again. I was pretty bad at this last class. I'm going to try it again. Because, the real reason is I just learned how to change the scale, and I think we can make the basketball look better. Let's try it. So if I do this. Oh, that's not bad. Okay. If I say stop, does it erase? No. No. Sample. It won't let me click that. Ah. Nope. Wait. Keep sample. Probably saving it somewhere. Oh well. I'm gonna change this. Oh, I locked it. That's it. Lock scale. All right. Oh, thanks. Shoot. I'm gonna try that. Wait. Okay. Hold on. This thing's not gonna let me do it. Okay. It's gonna start scaling on me. Hold on. Okay, I zoomed out, I got my scale nice, now I'm gonna lock it. All right, let's try this one more time. And now, of course, I'm gonna miss. All right, that's fantastic. All right, I'm gonna let it keep clicking because as soon as I hit stop, it's gonna erase. Okay, So here's what I wanted us to see. The ball's doing exactly that. So okay, let's take a look at this plot. I don't even, whatever you're doing in life, poetry major, anything, reading a plot is important. I think we got to be able to read plots, right? That's good. The news is going to show up some plot. They're always going to mess with the scale to try to make a point. We need to be able to read plots. So here's a plot of the velocity of the basketball. So let's take a look. At 0.04 seconds, it looks like I entered the frame, right? Then it was a negative velocity, because we're looking at velocity. Looks like I lowered the ball toward, that's probably what that was. I probably entered the frame, then I lowered it. And then I held it still for about a second. And then, so do you see it like, I guess that's like right about 1 second, right in the middle. I give it this nice vertical acceleration. That's that vertical part right here. So the velocity just increased. The velocity was 0 for about a second, and the velocity went up. So this acceleration of the basketball can be seen as the slope kind of shooting up like that. That was me accelerating. I have no idea what the value of that acceleration is. It doesn't matter. Here's what I wanted us to see. As soon as it left my hand, it was moving up. It had a positive velocity. So it left my hand with a positive velocity. That's off the map somewhere. Hope I don't screw anything up by doing this. Oh, nice. All right. That is really good. Okay. So that's initially, you see a couple data points. That's me accelerating. As soon as it leaves my hand, that's what you're looking at right here. That is not the peak of the ball's flight. I want to make sure we're clear about this. What we're looking at is a velocity plot. So that point at the way top is actually the second it left my hand. Then what you're seeing is as soon as it leaves my hand, no one's touching it. It starts slowing down. That's the values decreasing each 20th of a second. Each one of those dots. Every 20th of a second, it's going slower, slower, slower. And then you can see at 1.6 something seconds, it hits the horizontal axis. What's it doing there? It came to a stop for an instant. It went up in the sky. It went slow, slow, slow. It came to a stop and then came right back down, accelerated right back down. Notice there's just a beautifully straight line. And again, I don't care what your major is. That's a beautiful plot. You should see beauty in a good physics plot. That's just right through that is awesome. So it slows down, slows down, slows down, gets to a stop, speeds up, speeds up, speeds up, completely constant the whole time. That's nice. So I'm going to leave that. The clicking is going to get old. Can you guys hear that clicking? Oh, well, I'll let it go. Yeah, probably from there. Is that annoying? Not too bad. All right. I'll leave it. I'm going to take a screen. I don't, yeah. Print screen. Okay. I'll save that for later. All right. There it is. Okay. So what we just watched, we watched that ball accelerate way better than I ever could have. I've been up here for 2 periods, 2 classes now, trying to get a nice acceleration, and there's no way I could do that. Basketball did it great. It just decelerated at a constant rate the whole time. Okay. I want to talk a little bit about what that is and why it's doing that and why we care. Just briefly before we get back to the basketball, I mentioned last class that occasionally we might want to quantify things in this class, and it being America, we are usually most of us are most familiar with feet and pounds and things like that, and I tried to make the argument last class, and I'm going to stick by this. That's insane that we do that. They are terrible units. The metric system is just so nice. So scientists for a long time have adopted the metric system. I wish we all would. It just makes our whole life a lot easier. Can you imagine? So my cousin is from Denmark, and so when she emails me a recipe, it's all in grams and what, centiliters or something like that. It's so easy to double and triple. Like, if you've ever been, I don't know how often you cook, but if you're like, oh, the recipe calls for 2 or 4 teaspoons, I want to triple that. Oh my gosh, I have to, it gets difficult. I think it's a crazy system, like cups and pints and stuff like that. So if everything's in just centiliters or cubic centimeters or something, everything, your life is just way better. So anyway, in this class, we're often going to talk about the metric system. That's usually how I go. So when we talk about distance or displacement or length or anything, I'm usually going to use meters. I think everyone knows what a meter is. It's yay big. For mass, when we're talking about mass, here's one of the things that's nuts about the English system or the imperial units. In the English system, mass is measured in pounds. Force is measured in pounds. So it's 2 names for 2 totally different things. It's bonkers. And so, yeah, so we're not going to, that's nuts. So for us, we're going to use, for mass, we're going to use kilograms. And for force, we'll use newtons, named after the guy Newton. So 2 different, there's a great idea. Let's just name them differently. So for mass, how massive something is, we're going to use kilograms. And in English units, we measure time by seconds. And in the metric system, we'll use seconds. It's good. It's a good. That one's pretty good. That one's pretty good. Incidentally, I don't know if you know this. Second here, a second is the second division of an hour by 60. That's why they call it second. Also, fun trivia, if you're interested. The meter. So science has decided to throw out the whole imperial units and come up with a better system. And so they got the metric system, which is great. But another thing that they did that was great is they tried to universalize it. So when I'm in a lab in Copenhagen or I'm in a lab in Tokyo, I don't have to wonder what a meter is. It's universal. So no matter where you go, you can buy a meter stick. It'll be the same length. It's pretty important that we've done that. And in order to universalize it, we've actually boiled most of our units down to fundamental physical quantities. So you want to know what a second is. If I'm in my lab in Tokyo, if I don't know what a second is, I have a fixed, I don't even have to, I could be on the other side of the galaxy. On the other side of the galaxy, I could tell you what a second is. And so we've boiled it down to things that will exist in the whole universe. So if I were to meet an alien, I could say, you know what a second is? It's 9 billion oscillations of the energy levels of a cesium atom. And that alien would say, we have 9 billion and we have cesium, so I know exactly what you're talking about. The meter is actually just how far light goes in some fixed amount of time, I forget. So light, again, if I ever met an alien, I'd say, you know that thing light? Yeah, well, how far it goes in 1 nanosecond, or I think 3 nanoseconds about, that's a meter. And so an alien would have light, and we had just discussed what seconds are, so yeah, the alien could do that. The only one we haven't boiled down to a physical quantity yet is the kilogram. And so what we have is a kilogram, and it's in a museum somewhere, or a science lab somewhere, there's literally just the kilogram. So if I want to know what a kilogram is, I have to go use the kilogram. And it's not a great system because I have to go to the kilogram. And now they've made replicas, so now there's like 20 of them, but still, I got to compare my kilogram to something. And that's difficult because I have to go there. And if I'm talking to an alien on the other side of the galaxy, they have to come to, I think that one's in Maryland. That's a pain. But also, it's not constant. It interacts with air, and it gets a little bit heavier over time. So they have to go in there, and they actually have to clean the thing to try to get it exact. So they're trying to get the kilogram down there. They've got some ideas. One idea right now is a certain number, like 80 gazillion silicon atoms will be 1 kilogram. So I just need a ball of silicon that's a certain number. But how do you count out 80 gazillion silicon atoms till you're up to a kilogram? The idea is, well, if a sphere, I could tell you the volume of the sphere, and I know, but then how do you make a perfect sphere? So it's going to be tricky. I got my vote on the watt balance. It's a whole other idea, but we'll see how it goes. All right, so anyway, this class we're going to use MKS units, meters, kilograms, seconds. And so when I'm describing velocity, I'm going to say meters per second. I don't want that to start to lose its meaning. Like I said last class, I think miles per hour has started to lose its meaning. And so people say, I'm going 80 miles an hour. That is miles. That's a distance per time. So when you say miles per hour, you're saying a unit that's distance divided by time. Miles divided by hours. That's what miles per hour means. So when I say velocity, I'm saying meters per second. That's how many meters I go every second. And then when I say acceleration, that's the slope of my velocity plot. That's how many meters per second I change every second. Or meters per second, or meters per second squared. So the units for us are going to be meters per second squared for acceleration. So if I'm going 0 meters per second, let's look at like, we'll use that top one. The top one say I'm going 2 meters per second, and then 4 seconds later I'm going -2. Too many numbers. Anyway, 4 divided by 4, right? I went -1 was my acceleration. I changed my velocity 4, that's the meters per second part, in 4 seconds. So 4 divided by 4 meters per second, divided by 4 seconds, it's 1 meter per second or meter per second squared. So if next time you see, and one of the reasons I just want to even say this is next time you see meters per second anywhere in any kind of literature, I want you to know what that is. That where the squared come from, because you're measuring something that the change in something that already had seconds in it per second. All right, that's enough of that. Any questions? Okay, we got to get to where that basketball got its nice constant acceleration. We've got 10 minutes to do that. We can do that. So here's an equation that has too many numbers in it. So we're not going to use it for calculating. We're not going to use it for calculating, but I do want you to see it. And here's what this equation is telling us. And I'll call this is often called Newton's universal law of gravitation, or sometimes I just call it Newton's fourth law. Here's what Newton figured out, which is a big one. Everything attracts everything else. Believe it or not, you and the person sitting next to you right now are experiencing a mutual attractive force. It's true. It's true. You may feel it. I don't know. I feel it. But it's there. It's there. It's guaranteed it's there that you and the person next to you are experiencing a mutual attractive force. That's the M1, M2 up there. M1, that's you. M2 is your neighbor. You guys are pulling on each other, and it's measurable. It's actually measurable. That force, and the only reason I want to bring up the equation, not that we're going to have to calculate it, get our TI-83s out. The reason I want to bring that equation up is just to show you the relationship. The relationship is it's proportional to your mass and your next door neighbor's mass. It's proportional to that, so they're multiplied. It's proportional to some capital G. It's just a constant we don't need to know. And it's inversely proportional to the distance. So if you and your neighbor looks like are about 1 meter apart, there's a 1 on the bottom. If you were to move 1 seat over, now you're 2 meters apart, you've doubled the distance. You've actually quartered the attraction. So it drops off rapidly with distance. It drops off with the square of the distance. So the closer you get, it goes up with the square. It's exponential. So get close if you want to feel that force. So here's why that's relevant to us. Here's why that's relevant to us. Okay. The force you are feeling right now in the bottom of your seat, the reason you are stuck to your chair right now, is because you are experiencing a mutual force between you, let's call you M1, and something else. That something else is the planet Earth. Now, the force between you and your neighbor is probably not huge because most humans have a mass not that huge. The Earth has a mass that's something like 6 with, I think, 24 or 27 zeros after it. It's a lot of mass, so it adds up. It actually can result in a pretty big force. So the force you're feeling in your seat right now is the product of, let's call this capital G. This is the mass of the Earth. This is your mass. And this is the radius of the Earth squared. So I use the radius of the Earth because you're not touching the Earth right now. You are 1 Earth radius away from the Earth. Because the center of the Earth is down here. You're way up here. So you're 1 Earth radius away from the Earth. Here's the only reason I want to mention that today. All of these numbers are constant. Those are constant. So no matter what your mass is or whatever we're talking about, if it's near the surface of the Earth, it's going to experience a force equal to its mass times all that together. All that's constant. We can tie all of that together and call it lowercase g. Lowercase g is the acceleration due to gravity. So the acceleration due to gravity comes from the fact that you're sitting 1 Earth radius away from a planet called Earth, and so is everything else on the surface of the Earth. So we all are experiencing the same lowercase g, because we're all near Earth, the same mass. So my Earth has the same mass as your Earth. I'm the same distance from Earth as you are, and capital G is just a universal constant. So that isn't going to change. So lowercase g is the same for all of us. That lowercase g turns out, we can explain this maybe more next class, to be an acceleration. That acceleration is what was the slope of that plot that the basketball made. That nice, perfect, smooth, straight plot we saw, that was the slope due to capital G, mass of the Earth, radius of the Earth squared. All that together makes it just do this nice acceleration. Now, the reason I'm going to have to do that more next class is because I have to get to this, because it's been up here the whole class. I really want to play with it. And this might be the last thing we do. Inside here this is a tube. It's got air in it. And there's 2 objects in here. Yeah, there's a nickel. You may have heard that nickel just hit the bottom. And there's an orange feather. Let's see. Let's go. That's probably not going to help. Can we see, can you see the orange feather? There's an orange feather in there. Okay. So this orange feather and a nickel. And I think you can tell by the sound, the nickel falls at about the same rate as anything else on this Earth. It just falls down. But the feather takes forever, right? And we'll talk more in the next class about why that is, but I think you'd probably know there's something called air in here, so the feather takes forever. So every time I turn around, here comes the feather, nice and slow. Okay. Now, let's see if I can get this to work. If I were to take the air out, we're not used to seeing feathers. We're not used to seeing feathers fall at like a stone, but the only reason is because there's usually air. So if I can get rid of the air, in other words, get it a little over 760, let's see if it works. It's trying to make a perfect vacuum. Not possible. But that's probably pretty good. Okay, let's see. The orange feathers right there. Not bad. Not bad. I think I could do a little better. So it's getting close to falling like a rock, right? That's pretty good. Hopefully you can see that. Boom, that was a pretty good one. Thing falls like a rock. And so this to show you that everything, big, small, feather, nickel, bowling ball, whatever, is going to fall on the surface of the Earth at the same rate, because we're all sharing those same quantities right there. And so I think it was Galileo who stood Leaning Tower of Pisa or St. Paul's Cathedral or something and was dropping big balls and small balls off and said they all fall at the same rate. That's crazy. That's what's going on here, because they're all undergoing the same force. Let's see if I can take a little more air out. We'll do it one more time, then we'll call it a day. Actually, I'll do it one more time before we pack up. I did want to, it's too early to pack up. It's 44. We can go 2 more minutes. I did want to mention, I think this morning, updated your iClicker grades in Colab. If you have a 0 for your iClicker grade in Colab and you don't think you should, please do two things. First, check and make sure your iClicker is registered either through Colab, you can do it, or if you're using the app, please make sure your UVA computing ID is in the app under settings or something, or profile. That's how I know who you are, is your UVA computing ID. If that's true and you still don't know why you're not getting credit, shoot me an email. We'll try to figure it out. But I think we're up to like 240 some people in this class. I think there's still like 60 people that have 0. So either, I mean, there's a lot of empty seats. So maybe there's 60 people just aren't here. But I don't want you to be thinking you're here, and I don't want you to be here and me not know it. So let's try this again. That's probably as good as it's going to get. Last time. Oh, that's a good one. That was a good one. Okay. That was like almost exactly the same time. I'm pretty happy about that. And it's hit, I think the feather just hits the side more often. Once the feather gets going, it's going. There. I meant to do that. Okay. I could do this all day. Okay. Any questions? See you Monday.